right, hello everyone. Welcome to today's lesson. Today we're going to be kind of continuing off of what we learned last week. So last week we were focused mostly on numbers. Today we're going to be talking about exponents and radicals. We're going to be covering squares, cubes, and roots. We're also going to be doing some population growth calculations. And we're going to learn about fractional exponents and entire and partial radicals. So let's start off with some vocabulary. A perfect square is a number that can be expressed as product of two equal factors. What this means is that if you have a number and you multiply it by itself, then the number that is the product of that is called a perfect square. There are a few examples I've given you. So 0.4 times 0.4. So 0.4 squared is equal to 0.17. 0.4 can also be written like this. 0.4, a little floaty 2 at the top, equal to 0.6. 0.17. And we also have 12 times 12 is equal to 144, which can also be written as, let me draw a semicolon, 12 squared equal to 144. Okay, and next you have a square root, which is one of the two equal factors of a number, basically like the opposite of a perfect square. So going back to this, we have the square root of 196. So this square root symbol is actually supposed to extend all the way above the 196, but because the computers, they aren't really formatted to do this, yeah, when you're handwriting, you would have to write it like all the way above. So in a computer, in order to show this, you're actually supposed to put the 196 in brackets beside the square root symbol. That just shows that it's the square root of 196, not like the square root of 19 or the square root of 1 times 96 or something. So if we think back, if we kind of think of this in the opposite way, 14 times 14 is equal to 196. So if we want to take out that 14 back from 196, we take the square root of it. Okay, next, a perfect cube is a number that is the product of three equal factors, which is basically like a perfect square times that factor one more time. So over here we have 5 times 5 times 5, which is equal to 125. It can also be expressed like this, 5 a little floaty, 3 at the top. It's equal to 125. And the cube root is also just the opposite of a perfect cube. This cube root of 2.36 is equal to 6, is it? Might have to fact check that because I tend to make a lot of typos when making these. The cube of. Oh yeah, that is definitely wrong. 2.36 to the power of 1/3. Yep, made a mistake here. This is wrong. Let me give you another example. Let's just build off the one from the top. So if we have 125 and we want to get back 5 from it, we just put it under the cube root. Equal to 5. Okay. A prime factorization is the process of writing a number as a product of its prime factors. So basically breaking down a number into the prime factors that make that number. So for example, we have 24, and if we want to prime factorize that number, it would become 2 times 2 times 2 times 3. So this can also be written as aka 24 is equal to 2 to the 3 times 3, because 2 is multiplied by itself 3 times, right? So that is the same as 2 to the power of 3. Okay, let's move on. Representing perfect squares and cubes visually. So yes, it is actually possible to represent these numbers or these concepts visually. So if I told you to draw and label a visual representation of 4 squared, what would it look like? Well, a square is basically just, it would look just like a square, with all the sides equal to 4, because 4 squared is a 2-dimensional object, right? So each of its sides, let me grab a different colored pen, each of its sides equal to 4. 2D object square. Yes, it would be a square. Next, we want to draw and label a visual representation of 5 cubed. So, kind of the same idea. A cube, if you multiply a number by itself 3 times, you're basically multiplying it in 3 dimensions. So we have the first dimension, a line, the second dimension, then the third dimension, which is kind of extending back or at you, depending on which you look at. And so you basically draw a cube. I want to try to draw this as well as I can. That did not turn out very well. But it is a cube. You get the idea. 5, each of its side lengths are 5. This is a 3D object. Cube. All right. So the last question is, are there non-perfect squares that lie between 3 squared and 4 squared? Well, to answer this, let's first draw them out. So a 3 squared will look something like this. I'm gonna grab a different color for 4 squared. 4 squared will look like this. I've drawn them on top of each other. So right now there's think of it as a 3 squared inside of a 4 squared. So the purple would be the 3 squared and the orange would be the 4 squared. Well, you can see that it is possible to draw other squares inside of, in the space between. For example, the yellow part. This could be something like 3.5 squared or something like that. So yes, there are actually non-perfect squares. Non-perfect squares means like numbers that aren't integers, so squares that aren't integers that lie between 3 squared and 4 squared. Right. So now let's do some evaluation. Over here, you've been given a bunch of numbers, and we're going to take a look at ways to simplify. I want to say simplify, but it's more called evaluating. All right. So I'm going to grab a color. First, what is negative 4 squared? Notice how in these two, that was a very bad curly bracket. In these two, one has 4 has the negative and the 4 inside brackets, and the other doesn't. So the difference between these two is that in here, 4 is the base. Base is 4. But over here, the base is negative 4. So how does that affect the value? Well, in this, we can think of it as the negative is outside, right? So first, let's just do 4 times 4, which is 16, and then we add the negative back in, which would be negative 16. Next, in this one, we actually have to multiply 4 by itself twice, which would give us 16, because a negative times a negative is a positive. So in the first one, the 16 is negative, and the second one, the 16 is positive. So be very careful of where your negative sign is. If it's inside the base, then you're multiplying it by itself, which will always make it a positive number. But if it's outside the base, then you multiply the base first, and then you re-add the negative back in your final answer. Okay, next, you have 3 squared divided by 12, which would be, it can be rewritten like this, over 12. 3 squared, so 3 times 3 is 9, over 12. Now this is not our final answer because this can actually be simplified further into just, so you can, both the numerator and the denominator can be divided by 3, which will give us 3/4. All right, next you have 3/4 to the power of 3, so 3/4 cubed. This might look a bit daunting, so I'm going to draw it out in this format. So whenever you have a fraction to a power, remember that the power distributes into both the denominator and the numerator. So what this will look like is it will just be 3 to the 3 over 4 to the 3, which would be, so 3 cubed is 27, 4 cubed is 64, I believe. Let's see, 4 times 4 is 16, 16 times 4, 64. So can this number be simplified? Well, can it be divided by any of the factors? Let's see, so I don't think it can be simplified. 64 is not a multiple of 3, nor is it a multiple of 9. So I think this is our final answer. I tend to put my final answers in boxes because it just helps it look a bit neater and help the teachers, when you're writing a test, help the teachers see the final answer easier and mark it faster. So over here, we have 16 times 32 all under a square root. Just a reminder that when you're handwriting this, you do need to extend the square root over the number. But since this is in a computer format, I put them in brackets instead. So let's kind of work through this step by step. First, let's condense the number under the square root, which is 16 times 36. So in your calculator, you can just type in 16 times 36, or you can do it in your head if you're really good at mental math. So this would be the square root of 576. Yes. Normally you would, if the number doesn't divide well, you would leave it in this format. So the square root of 576 is 24. So it does become a very nice integer. So we're going to simplify it even further into 24. But if it's something like the square root of like 13 or something, then you wouldn't, you would just leave it like that because the square root of 13 is some horrible decimal number. Yeah. All right. Over here we have the cube root of 27 divided by 5. So the cube root of 27, let me write it out this way. The 3 goes just like it floats over the top left of the cube root, called the index. We'll talk about that later. Cube root of 27 over 15. All right. Earlier we actually did talk about we did explore the cube root of 27. So over here, when 3 was put to a power of 3, it became 27. So when it's the opposite, when 27 is put to the root of 3, then what's going to happen? What number is going to turn into? Well, earlier it had a base of 3, so this time it's going to have an answer of 3 over 15, which can be simplified into 1 over 3? No, 1 over 5. So we're multiplying both sides by 3, so 15 divided by 3 is 5. All right, I forgot to box my final answer earlier. Okay, now moving on. This time we have a variable in our answer. A variable. Wow, this is getting really crowded. You have the square root of 25x to the 4. So, all right, I'm going to rewrite this because this is looking really, really messy. Okay, so when we have numbers like this, in order to find the square root of it, we first want to kind of break it back to its prime factors. That's why prime factorization will be a really key skill in this unit. You'll be using it a lot to figure out the square roots and square cubes of numbers. Okay, so I want to kind of write in the top corner. 25, we want to find the prime factors of both these numbers. So 25 we know, or hopefully we know, it'll become 5 times 5 once it's broken down into its prime factors. That looks like a Japanese character. Okay, so 25 can be broken down into 5 times 5, but x to the 4th is broken down into 4 x's. X times x times x times x. So from these, we can figure out that right now, what would multiply to give us 25? So if we take out one of each pair, so we have 2 pairs of x's over here, right? So we can take out 2 x's here. We take it out, then it doesn't stay under the square root anymore. I don't know if this makes sense or not, but you'll see what I mean later when we kind of talk about roots more. So I'm going to bring it out from under the square root. I'm going to bring out a 5 and also an x squared. This will give me 5x squared. All right, moving on. We have 4 divided by the square root of 144. Now, if 144 doesn't hit you as a number, as like a special number right away, then I'll give you a little hint. The square root of 144 is 12. 12 times 12 is 144, so the square root of 144 is 12. This means we get 4 over 12, which can be simplified into 2 6 1/3. All right. Next one, I'm going to clear off this. We have the square root, or the cube root, sorry, of 1 divided by 125. So draw this out in a format that we're maybe familiar with. Right now, 1 over 125 is under the cube root. So from this, kind of like the one earlier where we had a fraction to the power, over here when we have a fraction to the root, we can actually distribute this root into each of the numbers, so the numerator and the denominator. This would look like this. Over 125. So now we just figure out each of the numbers individually. The cube root of 1 is easy, it's just 1. And then the cube root of 125, it might not hit you right away, but it's 5. You'll start to notice these numbers after a lot of practice. All right, so our final answer is 120, or 1 over 5. Okay. Now we have something that looks really scary because it looks so long. But once again, we can condense everything under the radical. What I mean by condense is just multiplying it all together. Multiply. So what this gives us is the cube root of 1 times 8 is 8 times 27 is, let's see, 8 times 27. You can do long multiplication or you can grab a calculator. For the sake of time, I'm going to grab a calculator. It gives us 216. And we still have the variables, which we can't really multiply by anything, so we're going to keep it in here. Okay. 3, 6. All right. Similar to what we did for an earlier question, we have to first find the factors of the inside numbers. Find factors. Prime factors, I should say. So for 28, well, I'm going to kind of draw this aside. For 28, it will be, well, we can first multiply it by 2 to kind of get rid of that. It becomes, let's see, so 216 divided by 2 is 108. And this can also be, this is even, so we can also take out another 2, which will be 54. This is also even, so we can once again take out another 2, which leaves us with 27. And 27 can be broken into 3 and 9. So 216 is equal to 2. 1, 2, 3. 3 times 2 to the power of 3 times, what's this? 3. Oh, but 9 can also be broken down. I shouldn't circle it. 9 can also be broken down into 3 times 3. So we have 1, 2, 3 3s. And this is very convenient for us because 216 is just 2 times 2 times 2 times 2 times 3 times 3 times 3. Then we can just take out a 3 from each group of, or we can just take out a number from each group of that number, which means in 2 there's one group of 3 2s, so we can take out 1 2 from that. Take out 1 2, and in 3 there's in this number there's 1 3, or we can take out 1 3 from this group of 3 3s. Yeah, very confusing. And take out a 3, which means we can get a final answer of, oh, we didn't even deal with the variables yet. So same thing for the variables. In this group, we have a times a times a, right? So we can take out 1a from that group of 3 a's. And for b, it's b to the power of 6. We can take out actually 2 b's from those 2 groups of 3 b's. Very confusing, I know. It'll make sense soon, I promise. So what this means is that we can take all these out from under the root, which will give us 2 times 3 times a times b squared. Let's simplify this into 6ab squared. This is our final answer. All right. Okay, hopefully this made sense. We'll do a few more calculations like this later. So if you still don't fully understand it, you can do a few worksheets or you can drop into a tutorial. All right. Kind of go to the next slide. Exponent laws. So we did actually go over exponent laws in grade 9, but not we, I guess, but you and your grade 9 teacher. So exponent laws are basically just rules regarding each type of exponent, kind of like how we see over here we have multiplication, right? So an example would be a to the power of 3 times a to the power of 5. When we expand this, it'll become a times a times a times a times a times a. Might seem really obvious now, but what this would turn out to be once you simplify it is just we count up all the a's in this group. So a times a times a times a times a times a times a to the power of 8. So that lets us conclude that the exponent rule is just a to the m times a to the n is equal to a to the m plus n. Next, we have division. Once again, let's write it out in expanded form. When you have this, you'll notice that you can cancel out 2 a's because when an A is over an A, it just becomes 1. So A over A is equal to 1, right? So 1 is redundant, which means we can kind of, quote, cancel it. Once we have that, we're left with a to the power of 4. So we can conclude that a to the m divided by a to the n is equal to a to the m minus n. Okay, over here we have a power law, which states, so over here we have a to the 2 to the 4, which means that a to the 2 is multiplied by itself 4 times. When we expand it out, it looks like this. We can count up all the a's, which will just give us a to the 8, which means that a to the m to the n is equal to a to the m times n. And for a power of a product, kind of the same idea as the power law over here, except we've just have 2 variables that are being put to a power instead of 1. So a squared times b times a squared times b times a squared times b is just a to the 6 times b to the 3, because you count up all of these different variables, right? You can conclude this is the power law, or the power of a product law. Now we have power of a quotient, kind of the same idea as the top one. Just this group multiplied by itself 5 times, which when you count up all of the numbers or all of the variables will give you a to the 5 or b to the 15, which means this is the power of a quotient rule. Also, there's another one that isn't mentioned here, but any non-zero number to the exponent 0 is equal to 1. So it doesn't matter whether it's like a really small number or a really big number. Anything, if put to the power of 0, is always 1. So if we have 1 million to the 0, well, it's going to be 1. If we have 5,430 to the 0, it's still going to be 1. All right. So over here we have some practice questions for you to do. I'm not going to go through them in today's lesson, but you feel free to go over them at home. Just every question, it's good practice. You don't have to go through all of them, of course. If you understand this perfectly well, then feel free to just skip over. Okay, now we're going to do some application. So we learned about kind of the basics of exponents, but when do we use this in, quote, real life? Well, mathematicians often use exponents in population calculations, half-life or depreciation, which is kind of like population, and also interest, which is dealing with money. All right, we're going to explore all of these. So first off, population growth. At the top, the highlighted, it's you're given a formula for population growth, which states that Pn is equal to P to the P0 times B to the power of G. Now I'm going to talk about each of these variables. So B, which is the one in brackets, stands for the behavior. And that means how does the population change? Like, does it double? Does it halve? What's the behavior? So for example, actually we're going to be taking a look at some examples later, so I'm going to leave this for now. G stands for the number of growth cycles. So how many times is this population exhibiting this behavior? So maybe it doubles every week. So after 3 weeks, how big is it? So that 3 would be the number of growth cycles. The population N stands for the population after N number of cycles. So N is actually the same as G. I don't know why there's a different, or I don't know why they use a different variable for it, but essentially G and this tiny n subscript are the same value. Okay, and then P0 is just the starting population. So how big was your population at the beginning? We're going to put this formula to the test with an example in the next slide. So your colleague has been studying a colony of bacteria. You're going to be seeing a lot of bacteria in population growth calculations because bacteria grow really quickly, so it makes it easier to make word problems out of bacteria. Population doubles every 3 days. You take over the experiment at day 12, and the population number is 208. So how many days will the population be 1,664? Okay, let's first kind of write down the key information that we've been given. So usually the key information are the numbers. The population doubles every 3 days. So we have doubles and every 3 days. So kind of take a look at this. Doubling would be the behavior. So the B value. B value is equal to 2 doubling. And if we look back at our formula, what else do we have? G, the number of growth cycles. So how many days will the population be? 1,664. Are we given the G value on this even? So day 12 would be, what would that be? Let's see. Day 12. Are we looking for the, I don't think day 12 can be applied in this formula yet. We're going to have to apply it in a different way. So we're going to leave that value for now. And last one is, you take over the experiment when the population number is 208. So this 208 is when you first start calculating. So this would actually be the starting population, which means that the 208 would be your P0 value. Okay, and the PN, we are also given the PN, are we? So for question A, after how many days will the population be 1,664? So we want to find the G value of this equation, but we're also given the PN, which is 1,664. So PN, oops, I shouldn't write it here. What this would look like is, let's write out the formula. PN, so 1,664, is equal to P0, which is 208, times the behavior, which is 2, so it's doubling. And we don't know how many days it will take. So this days will be the X, or I guess I should use G. What we're gonna do here is, let's see, what's really helpful a lot is simplifying. So right now you're given a bunch of numbers, but we want to simplify it. So what can we do in here to kind of get rid of some numbers? Well, we can definitely multiply this or divide this both sides by 208 to kind of get rid of this 208. This will leave us with 1,664 divided by 208 is equal to 8. 8 is equal to 2 to the G. Now it looks really obvious because 8 is a number that we've seen a lot. What 2 to the what power gives us 8? Well, 2 to the 2 is 4, so 2 times 2 is 4, times 2 is 8. So in that, we've multiplied 2 by itself 3 times, which means that 2 to 3 is 8, which means that G is 3. We should double check. Is that our final answer? Yes, I believe so. Oh no, G is our growth cycle. So we can't jump the gun in this one because notice how it says the population doubles every 3 days, which means that 1 G is equal to 3. 1 growth cycle is equal to 3 days, which means 3 growth cycles would be 3 times 3, 9 days. So actually, instead of putting 3 in the final answer, we actually have to multiply 3 by 3 first because 3 days, which would give us 9. It would take us 9 days. Let me write this down. So 3 times 3 days equal to 9 days. All right. So it's really important to read the question and make sure you're actually answering the question before you answer the question. I'm going to circle this to kind of section it off. Next, we're given B. So what was the starting population? All right. So over here, you're finding the actual P0 value. Let's see. Oh no, you're not looking for the P0 value. Sorry, you're looking for the Pn value. But this time, the Pn value, you're actually going backwards, which means that the growth cycle will be negative. It's kind of hard to understand, but I will write it out to kind of, let's kind of process this information first. So we want to find the starting population. So you want to find when how big the population was at day 1. Remember you're kind of given a bit of information already. So you take over the experiment at day 12, which means that it's been how many growth cycles? You take over the experiment at how many growth cycles? Well, since the population doubles every 3 days, if we divide 12 by 3, so let's kind of just figure out G first. G is equal to 12 divided by 3, which is equal to 4. It's been 4 growth cycles. So you took over the experiment at the 4th cycle, which means if you want to go backwards, you actually want to find the equation with a power of -4. Let's just write this out first. So you are looking for the starting population. So P at n, and you were given a starting population of 208. And what is the behavior? Well, this part's really important because you are no longer doubling it, you're actually halving it because you're going backwards in time. So wait, let's keep the behavior at 2 for now, but we're going to put it to the power of -4. Now, whenever you have a number to a power of value, an exponent of a negative, you actually flip, you take the reciprocal of that number. It's a pattern. There's not really a specific formula for figuring out the negative. It's just a pattern. So just remember this, that whenever you have a base to the power of a negative, you actually flip it so you get a reciprocal. Box this off because it's important as well. So what this means is that we actually have 1/2 to the power of 4 rather than 2 to the power of -4. Which makes sense because if you're going backwards in time, instead of doubling, you're actually halving the population. The population will become smaller. So now we have all the values that we need to find Pn. What we got to do is just calculate it. So what we're going to do first is take the exponent, because remember the BEDMAS rule, brackets, exponents, and then multiplication and division. So we're going to take the exponent, which is just 1/2 to the power of 4, which will come 1/8, and then we take that 1/8 times 208, which will become 26. All right, so now we have our final answer. Starting population was 26 bacteria. 26. It stands for bacteria. I'm gonna once again section this off. Whoop, whoop, whoop. All right. Finally, we're at part C. How many days will the population exceed 13,000? All right. So there are a few ways to do this. We can do it with an equation, or we can draw a table. Well, drawing a table will be quite it'll be quite long, but let's try it to kind of see different methods, explore different methods of solving. So just for the sake of exploring different methods, we can draw a table. You could have actually drawn a table for the other two parts of this question as well, but it would take a lot more time than it would have with just with an equation. So let's try drawing out a table. In this table, we're going to need a value for cycles. We're also going to need a value for time. And we're going to need a value for population, which I'm going to shorten to pop. All right, so we want to find out how many days the population will exceed 1,000 or 13,000. So let's start at 0. Sorry, let's start at the first cycle, which we will remember from last time. Oh no, this is going to take a while, so let's just start at day 12, which is which cycle? 12 divided by 3 is 4. So at cycle 4, it's been how many days? 12 days, right? And our population was 208. Oops. 208. If we move on to the next cycle, so after 3 more days, cycle number 5, the time is now 15. Because there's one cycle every 3 days, the population is doubled, which means that the population is now 416. Next cycle, cycle 6, it's been 18 days. It is now 832. Cycle 7, 21 days. Let's see. 1600 and this is really messy. I'm writing so small, I'm sorry. 1600, or not 1600, 1664. Just kind of what we got for the earlier value for part A, right? But we're still not at 13,000 yet, so let's keep on going. 824, and double this is just 3,000. You can see that the numbers are increasing really a lot, because this is something called an exponential function. You don't need to know that yet, but you will learn about it soon. Next, we have 9 cycles. What is this? 20, 27. And then we have, numbers are definitely increasing a lot. 16 times 4. Sorry, I need to make sure I don't want to accidentally make a mistake. I'm going to type it in my calculator to make it faster. 6,656. Next 10, and then we have 30. Double that, we get 13,312. And at this point, we stop because we've reached more than 13,000. Right now, we're at 13,312, right? Oops, I think I added an extra 3 somewhere in there. Let me rewrite that. My writing is becoming messier and messier over time. So we stop here. 13,312. We've now exceeded 13,000, and it's been 10 cycles, 30 days. So 30 days from the first ever, from day 1, you finally exceeded 13,000. So is our answer 30 then? Well, not quite, because if we read the question again, it says, after how many days will the population exceed 13,000? Which means that we actually have to subtract 12, which is our original value, from 13, because 12, we took over the experiment at day 12, right? So we're counting day 12 as day 1 in our situation. So yeah, if we take away 12 from 13, we get, see, 8, 18. After 18 days, population will exceed 13,000. I think we're running overtime here. I'm just gonna keep on going. So now we're gonna kind of look at some half-life calculations. In case you don't know, a half-life is the time required for a quantity to reduce to half of its initial value. So over here we have a word problem. At 8 p.m., a vet has just administered a sedative to a horse that was traumatized during a traffic collision. Whoa. At the time of the dose, the concentration of the drug is 8 parts per million. I forgot a bracket over behind million, but half-life of the medication is 7 hours. So at what time the next day will the next dose be due if the concentration isn't supposed to drop below 2 parts per million? Well, let's kind of use the same formula that we were looking at before, which is the Pn is equal to the P0 times B to the G. So let's bring it out. What key information do we have? Well, we need to, so at the time of dose, the concentration of the drug is 8 parts per million, which means this 8 ppm is the P0 value, the starting value. The half-life of the medication is 7 hours. So which means that the growth cycle is every 7 hours, it will reduce by half. Let's see. At what time the next day will the next dose be due if the concentration isn't supposed to drop below 2 parts per million? I think that this is the Pn value. Now, what are we looking for here? Are we looking for the Pn? No, the Pn's already been given to us. We're also given the behavior, which is just half-life. B is equal to 1/2. So we're actually looking for the G value in this. And since G is in the exponent, it does make it a bit harder for us. But we will have to solve this. We can't do it algebraically. We'll have to do it by something called trial and error. So we're just going to try every value until we reach the G value that works. So let's kind of write down what equation we have. So Pn is equal to ppm, and the starting initial value, so P0 is equal to 8, behavior is 1/2, and the G is unknown. So in this, we have multiple ways of solving. We can organize all of our data into a table like we did for the last question. So let's try that. So in this table, we're going to have cycles. Sorry, not cycles. Cycle number. We're going to have the time. And we're going to have the dose concentration. All right. So at 8 p.m., we're going to call this hour 1. Let's just call it hour 1 for, let's just call it 8 p.m. What am I saying? That's cycle 1. Sorry. That's cycle 1. Well, we have to be very careful because it might be, cycle 0, because this is the P0 value. So at cycle 0, which is 8 p.m., the concentration is 8 parts per million. So after 7 hours, which is cycle 1, and the time will be whatever 8 plus 7 is. So we're going to count forward 8, 9, 10, 11, 12, 1 a.m., and 2 a.m. So at 2 a.m., concentration will be 4 parts per million. And then Is this our final answer? Wow, we've already come to the final answer and it's only been one cycle. Oh no, it does not. Sorry, my bad. It's not supposed to drop below 2 parts per million, right? So I think in the next cycle, it will be at 2. So this is where we stop because now our concentration is 2 parts per million. And the time is 10 a.m. So this is the answer. 10 a.m. So tables do really help, especially when you're trying to organize your information better. All right. Interest calculations. This is a really, really long question, but we're going to try to zoom through it. So interest is calculated as a percentage of a loan, blah, blah, blah. So basically what interest is, say you're borrowing money from the bank. You borrow $100 and the bank actually, like if they just lent out money to everyone for no reason, then they would be losing money. But that's not the case because banks want to make money, right? So they actually charge interest, usually monthly, for the money that you give them, or the money that you borrow from them. So your grandparents invested $10,000 on the day you were born. So the money is intended to help pay for your post-secondary, which is just university or college, and will be available to you when you turn 18, which is after you graduate high school, right? The money earns 5% per year, which is reinvested each year. So 5% is the interest, and the growth cycle is every year, or the time, I guess, is every year. So let's kind of take a look at this. Today is your 15th birthday. What is the value of the investment? I've given myself some blank space to kind of calculate because this will take a lot of calculation. Let's kind of gather all the information that we've been given. So 10,000 is the P0 value because that is the starting amount that we've been given, or that your grandparents have invested. Let's see, the money is intended to help pay for your post-secondary. That money earns 5% per year. So this 5% is the interest, which is part of the behavior, but there's something really special about the behavior because a percentage, we'll first need to convert this to a decimal, right? So 5% just equal to 0.05. Because you divide this 5 by 100. And we don't know the growth cycle. We also don't know the PN value. So I think the growth cycle will be given to us. So we're given 2 pieces of information. The behavior, which is, oh, it's not 0.05. Sorry, you also need to add in, because you also need to add in the original amount, which would be 1 plus the interest rate. All right, so this is all the information that we've been given. Let's move on to look at some questions. So today is your 15th birthday. What is the value of the investment? Oh, look at that. We're given the G value, 15. So let's take a look. A, also given the G value, which is equal to 15, which means we can draw out a nice equation. Pn we don't know, but we do know P0, which is 10,000, the behavior, which is 1.05. Also do know the growth cycle. So now it's just a matter of putting everything in your calculator. Pn is equal to 10,000 times 1.05 to the power of 15. This will give us $20,789 and a bunch of decimals. So let's round up those decimals to the nearest hundredth, because that's how cents work. And is equal to 20,789 and 28 cents. All right, B, let's move on. B says, what is the value of the investment? What will the value of the investment be when you turn 18? All right, so now 18, we're given the growth cycle. Now let's take a look. G is equal to 18. Which means we can write up another nice equation. En equal to 10,000 times 1.05 times 18. Again, let's put this in our calculator. 10,000 times 1.05 to the power of 18 is equal to 24,066. 24,066. And how many cents? 19 cents. Oh, wow, you've been given a lot of money for your post-secondary. All right, next part. If you don't need the investment and decide to leave it untouched until you graduate at age 22, what will the value be? So now the G value is 22. Once again, plug it into our formula. G is equal to 22. Same thing, Pn is equal to 10,000. You can probably work on this faster than I can write it out. And it's equal to times 10,000 times 1.05 to the power of 22, which is 29,000. That's a 9. Looks like a Y, but 29,252.60. Oh, nope. Rounded it wrong. It's actually 61. Oh, I forgot to add dollar signs for all of these. Let's see. Dollars, yeah, just know that they're dollars. All right, that's the answer for part C. Part D. If your grandparents had been able to invest money at 8%, what would the new values be for all of the answers to part A, B, and C? Well, what is being done here is that you're actually changing the behavior. So instead of 5%, your grandparents are now investing 8%. So 8% is equal to 0.08, which means that the behavior is now equal to 1.08. So basically just plug this number into all of the calculations from before to get a new value. All right, last question. E, if your grandparents wanted you to have 75,000 at age 18 and they could invest 12% per year, how much would they have invested on the day you were born? All right, so this is kind of changing things up a bit. We are now given the PN value, which is, what was it again? Like 75,000. So the PN is now 75,000. And they also gave us a different interest rate. They actually gave us 12%, which means the behavior is now, let's see, behavior is now 1.12. And did they give us any other new information? No, that's it. So age 18, sorry. We're also given a G value of 18. So even though this is kind of a different style of question, we still approach it the same way. We still put these numbers into the formula. Units times our starting value. Oh, wait a second. We don't know our starting value because it's asking how much would they have invested on the day you were born. So we'll give this the variable times the behavior, which is 1.12 to the power of 18, which is our G value. So Now we'll need to isolate our unknown. What we can do is just divide both sides by 100, or sorry, not 100, 1.12 over 18. Which will cancel this out and then leave us with, all right, let's calculate this. So P0 equal to 75,000 divided by 1.12 power of 18. 9,752.95. And that is our starting value. So, P0, 9. Oh yeah, I've been really inconsistent with writing these units. In a proper test, like if your teacher was testing you on this, you would have to write units on all the values, but notice how I've actually forgotten it for a lot of these. Like earlier in the 10,000, I was actually supposed to put units for them, but I didn't. Oops, let me add them on now. Always remember units, because otherwise other people don't know what you're talking about. And that's the final answer. We finished the entire thing in one page. I guess I didn't need that other page after all. All right. You actually have, it's really over time, so I think stay if you want, but I'll have to continue this. All right, so now we're moving into a new part. We're going to be talking about fractional exponents. So, you already know of one relationship that will undo between exponents and radicals. So the appropriate radical will, quote, undo an exponent, and the right exponent, or a power, will, quote, undo a root. So for example, 2 to the 3 under a root of, or under a cube root will give you 2. But there is another relationship which can make the calculations much simpler. So this is kind of what I was talking about earlier. So 2 to the power of 1/2 is actually the same as the square root of 2. So let me draw this out. When you have a number like this, the top becomes power the exponent also known as the power, and the bottom, actually let me use a different color. Let's try blue. Bottom becomes the root. Oh, I should say the index of the root. So what this looks like is that this number will actually become the square root of 2 to the power of 1. Normally you would leave out the 2 because it's kind of implied, and you would also leave out the 1 because it's also implied. This would leave us with the square root of 2. On your calculator, when you're evaluating this, for a lot of older calculators or scientific calculators, you'll need to actually put the power in parentheses. I have a little blurb talking about it over here, but yeah, you can read over it. All right, now that's basically it for fractional exponents. In a lot of math courses, this is an entire lesson, but we covered it in one slide. I hope you kind of understood that, but there's, once again, a few practice problems in the worksheet if you would like to go through them. Now we're going to be talking about entire and partial radicals. So let's take a look at some more vocabulary. A power, which was what I was mentioning a lot earlier. I don't know why I didn't put this vocabulary earlier because I did talk about it a lot, but a power is made up of a base and an exponent. So may or may not have a numerical coefficient. In the example of 4 times 3 to the 5, or negative 3 to the 2, For the negative 3 to the 2, the negative is actually the coefficient. I know it's sounds weird, but think of it this way. It's negative 1 times 3 to the 2. That kind of helps you remember it a bit. And a radical is made up of an index and a radicand. Oh, typo. Yeah, I forgot a D over here, but this is the radicand, the y value. And the index is this tiny floaty thing beside the root symbol. The root symbol is, but I'll call it the radical. All right, let's try a bit of this. So we're gonna talk a lot about exponential forms and radical forms. So fractional powers can be rewritten in radical form. It's not called evaluating because you're not really changing anything besides how the number is written. So what it shows over here is just basically 64 to the power of 1/2 is equal to the square root of 64. If we evaluate this number, it would become, what's this? 8, right? Because 8 times 8 is 64, so we're kind of working backwards. All right, next. Switching between entire and partial radicals. All right, so now we're actually going to be introduced to some new vocab. I should have put entire and partial radicals in the vocabulary, but I'll kind of explain it here. So they're basically just ways of writing the number. Entire radicals is basically when the number is, well, the entire number is written under the radical. So let me write this down. Let me add a little blurb to insert a text box. Entire radical. Entire radical. And the entire written under or inside, sometimes inside the radical sign. Partial radical. All right. Kind of flip through my teaching notes a bit to find what I wrote for the definition of partial. Let's see. Right, the partial radical is basically when you take out everything that can be taken out, and you leave the numbers that can't be square rooted into nice numbers inside the radical. So the partial radical is exactly what it implies. When there's a coefficient, number under a radical. So this number under radical can't be divided or can't be taken out. So we leave it in there. Let's do some practice here. Over here, we're given 2 to the 3 times the square root of 625. So let's figure out what the prime factorization of 665 or 625 is. That will help us better determine which numbers we can take out and which one. Oh, sorry, not which numbers we can take out, which numbers we can bring in, since we're doing entire radical first. So we want to bring this number. We want in entire radical, we want to bring the 2 to 3 inside the square root, which means we can literally just do this. If we square it and bring it inside, the value will be equivalent. So I want to bring this inside, right? This means we'll have the 655 times 2 to the 3 times 2 to the 3. The reason why we multiply it twice is because when we bring things inside the square root, we still want the value to be equal, right? But in order to the value to be equal while under a square root, you'll have to multiply it by itself. We kind of saw an example earlier where let me bring it back up to this. So this one. Yes, no, it wasn't. We kind of saw here that if a value under here is the same as the value outside here, then both of these will cancel, which gives it the value itself. That was not the best explanation, but let's kind of work through this question and you'll see what I mean. So I brought this 2 to a 3 inside, so it meant that I had to make it a square, like square it. So once you have this, you can kind of condense the stuff inside, which will just be 625 times 2 to the power of 6. Remember your exponents laws, which will give us 40,000. This is our answer in partial or entire radical. Sorry, I need to make sure I did this correctly. Oh no, wait a second. You see, there's something very confusing because in this, we're not exactly sure, or I didn't write it clear enough, whether the 2 was the coefficient and that made the 6 to the power of 5 under the square root of 3, or was it 2 to the 3 to the square root of 625? Yeah, that's something to keep in mind, but normally the coefficient would not have a power, because if it did, you wouldn't write it in exponential form. You would just write 8 instead of 2 to the power of 3. So I'm going to assume that I wrote 2 times the cube root of 625, which means that our answer here is wrong. Oh no! I have to erase this. So let's kind of go back to square one, add an index of 3. So this kind of just shows how important the index is, because if you get it wrong, then your entire answer is wrong. Let's kind of work through this again. This time we want to bring 2 under the cube root. So kind of the same thing, same idea. When you bring a 2, you have to actually multiply it by itself 3 times. Times 2 times 2 times 2, which is equal to, we do the same thing, we just condense it, which is equal to, let's plug this in our calculator, 5,000. That is a completely different answer than what we had before. All right. So now let's do partial radicals. So what a partial radical is that instead of bringing the 2 under the radical, you're actually going to take some parts from the 625 outside the radical. So let me clear this off a bit. Instead of bringing 2 inside, you're going to be taking 625 outside. Yeah, outside. All right. In order to do that, we'll need to first prime factorize 625. So I'm going to kind of do this separately. 625. Let's use the factor tree. Right here, we can divide it by 5, right? And that will leave us with 25 divided by 5, 125. But notice how it ends in 5, so we can actually take out another 5 from it, which will leave 25. Once again, we can take out another 5, which will give us 5 and 5. So when we prime factorize 625, we actually get 5 to the power of 4. Let's write this out. This is the same as 5 times 5 times 5. Right. And we have this. So what we can do now is that for every group of 5, let me grab a different color. For every group of 5, we can take 1 5 out. Oops, that was a very bad arrow. That was not any better. For every group of 5, we can take 1 5 out. So this will leave us with 5 times square root of 5. On the square root of 5, we leave it as a radical because it's a really ugly number. Like, it has a bunch of decimals and it's really hard to write down. It's like 1.7 something something something. The decimals are terrible. We leave this. We leave it in this form. And that's kind of why it's called partial radical, because part of it is in the coefficients and part of it is under the radical. Well, you might be wondering, well, isn't this also a partial radical? Because we have part of it in the coefficient and part of it in the radical. But the key thing is that the stuff that's under the radical can't be taken out. Like, it can't be taken out without being a horrible decimal. So in here, we could actually take out parts of the 625, which we just did. But this is just neither an entire or a partial radical. Okay, we just finished our first conversions. Let's kind of move on to the next question. 3 to the index, I want to assume 3 to the 4. 3 to the, what's this? The root 4 of negative 36. So for the entire radical, we want to bring the 36 inside. What this would look like is negative 36 times 3. Oh no, that's not. The index is not 3, my bad. It's actually 4. We actually bring this inside, 3 to the 4, which would give us, let's see, negative 32 times 3 to the 4 is equal to negative, oh no it's not, because bracket is part of the base, so it actually changes our answer. It's not positive, or it's not negative, it's positive. All right, I'm gonna kind of erase this. Negative 32 times 3 to the 4 is equal to 2,592. That is our answer in entire radical form. Now for partial radical, we kind of do the same thing as we did for the last one. We have to first factorize 32. So we have negative 32. We can see, we can take out a 2. Let's take out a negative 2 just to get that negative out of the way. And we have 16. And this can be divided further into 2 and 8, which can be 2. Oh, times 2 times 2. Oops. So this number is basically just 2 to the 5 with a negative. Sorry. Okay. What this means is we can write this as oops. I'm gonna take the 32 out, right? So every group of 2, every group of 4, we can actually take out, oh, right, these are actually all negative values because in a square root, the factors can't be different. We have negative 2 times negative 2, times negative 2 times negative 2 times negative 2 This will give us, we can take out, for every group of 4, we can take out 1, -2. Over here we have a group of 4. Oops. We can take out a -2, which will give us -2 times -2. All right, and that's our answer. And to the end of the lesson. Wow, this was a really, really long lesson. Yeah, normally this would take weeks or so, but we did go over time today. Apologies. But yeah, it's a lot to process, I know, but there's still a worksheet you can practice, or you can drop into tutorials or email us at pilotprep.alberta@gmail.com. You can help with all of these. So yeah, hope you enjoyed today's lesson. Next week, we're going to be starting a new unit, polynomials, and that unit is actually going to be broken down into 3 parts, so 3 lessons. That's about it. See you all next week.